Welcome back. Welcome people who are new, and welcome back people who have been to our previous installments. We have been in somewhat of a winter hibernation, but we are restarting this seminars now. Today we have a few new people, and you might have not seen, and also a new interesting topic. As people go, please welcome Tijs and James. There should also be Majid, but I don't see him in the group yet. I guess he'll join later. And today we'll be talking about how to apply reinforcement learning to optimizing traffic flows and traffic signals. It's a topic I've been interested for a while. One of the first things you notice when you move to the Netherlands is how smart the traffic lights are. I'm not sure if they are using reinforcement learning at the moment. Probably they aren't, but it's still a big difference from all other traffic lights I've seen anywhere. So I've been looking to dig into the topic for a while, and we have speakers today who have been working on this research professionally. So without further ado, I'll probably give the floor to them. And at first, Tijs van Bakel will give us a short introduction to the field.
Yeah, that's right. Thank you, Vadim. So I'll try to share my screen here. And I hope that's visible to everyone. So there.
Visible to me, so.
Great. Well, so I prepared a small introduction to help bridge the gap between the audiences that we might have here today. I think on the one hand, we have people who are quite familiar with reinforcement learning and would like to know a little bit more about traffic applications. On the other hand, I've invited some people who are familiar with traffic management, traffic optimization, and they just want to know what all the fuss about reinforcement learning is. And for those familiar with both areas, it's just a short presentation, very high level, to give you an idea what we're going to discuss today. And the presentations that will follow will go in way more depth, I assume, and that might be interesting to you as well. A bit about myself. I'm Tijs van Bakel. I'm a researcher at Technolution, and I focus there mostly on traffic management. Technolution does way more than that, but today it's traffic management that I'm interested in. And I'd also like to say that I share my time between two jobs. I'm also a visual artist, something completely different. And as an artist, I focus on taking my art career very seriously. So that's why I jammed in a slide on my art career as well. If you're interested in that, I make photorealistic drawings, and you can have a look on my website or Instagram account. But back to traffic management. What that is all about is basically you want to optimize traffic flow, but it's slightly more involved. Governments want to implement their policies, and they can be very broad. It could be related to safety, road safety, for instance. Of course, I have to say that we're focusing on road traffic management here today, not network traffic management. And there could be environmental issues. There's also very different kinds of modalities, as they call them, that use roads, such as bicycles, pedestrians, cars, public transport, you name it. And the big puzzle is to prioritize all these when they're using the same network, and can be quite involved. And in this optimization, there's different cycles of optimization. For instance, if you look at the longer term, then you could even add or change road infrastructure. You could add devices. You could do all kinds of things, but I'm mostly interested in the short-term cycle, where you have these devices that sense information, and you have actuators that can do something with it. And I think Technolution is particularly good at managing all those devices to ensure that it works 24/7. But more and more we see that we are adding automated control to these devices, and that's where reinforcement learning comes in. So we'll continue with that. We zoom in a little more to urban traffic optimization, which I find particularly interesting because the networks are quite involved. You see a lot of different types of road users, and the most prominent here type of control that you have are the traffic lights. And the sensors are also quite diverse, but typically in the Netherlands, we have a lot of loop detectors in the roads that detect when a big chunk of metal, say a car, is on top of them. And more recently, our devices in our pockets are sending out a GPS signal. Well, not the GPS signal itself, but the position. Send it out to a data center, and we can observe a lot of data about where people are, how many people there are, and what speeds they're driving. And then the interesting thing is to combine this data into a control loop. And classically, traffic light has just been looping through a fixed program, and that works up to a nice extent. But there has been a lot of research to improve flow of traffic by combining sense data with a smart actuation policy. And recently, reinforcement learning is perhaps becoming a very good contestant there. So for those who are not familiar with reinforcement learning, I'm going to spend one slide on it. This is the canonical image that you'll see in every book. Basically, there's two items that are interesting. There's the agent, typically a robot in my head, but could be anything. And there's the environment. The environment could be a game of chess. It could also be an entire road network with all the cars driving around in it. And the model that we use is typically that the environment gives you a certain state. It's typically a vector of numbers. That could be the positions of the cars. For instance, if we're looking at a traffic light, it could be the length of a queue waiting in vehicles. Could be all kinds of things. But you put it as input to the agent, and then at every time step, it will decide what to do with this state. It will perhaps do nothing, or perhaps it will change and give another lane of road traffic some green light so that they can pass. This again will affect the environment, and the cycle is completed, and the environment will update and give a new state. And now the vital thing, which we will hear about later in I think the second presentation, is it's quite important to come up with a good reward system. For instance, if the queue lengths are shorter or if the waiting times are shorter, you could give the agent a larger reward. And now the entire thing about reinforcement learning is the goal to find a policy that optimizes this total reward over time. There are many, many different algorithms for this, quite different, but as Vadim will probably say, they're all the same and all very related. But to me, it's still quite a fuzzy bunch of algorithms, and I don't know which one to pick for which algorithm. So that's really interesting to look forward to. And now if you combine this reinforcement learning with traffic optimization, as I suggested, traffic light control lends itself to this. A traffic signal controller would be an agent, and there's quite a few papers out there that describe how this would work then. But you could also have, say, traffic management systems for an entire city or a bigger network use reinforcement learning to optimize traffic throughout an entire network. Whether this is feasible and what you should do is still open research, I think. And I've also found something interesting where you take only one vehicle and put a controller or an agent into that to help optimize the rest of the traffic. It's quite interesting aspect there as well. Now you see a lot about deep reinforcement learning. That's basically reinforcement learning with deep neural networks applied to them. And once you say neural networks and reinforcement learning, it means that you have to do a lot of training, and this requires simulation. And we'll see a lot of that again, probably in the next presentations. And for today, we have two presentations, the top papers, reinforcement learning benchmarks for traffic signal control. This is very interesting. It gives us a benchmark to compare various kinds of algorithms with each other. I think that's very valuable to the field. And the second one is probably a very good demonstration of how important it is to shape the reward, or to come up with a good function for the reward when you're doing traffic signal control. So I'm looking forward to both. And a third paper that I would just like to mention here, but will not have a presentation on it, is a reinforcement learning approach for traffic control by the Fraunhofer Institute. And I found it very accessible, and the fun thing is that they apply well, quite non-standard kind of reinforcement learning and apply it to two different approaches. One is a traffic signal control and the other is an autonomous vehicle. And I find it quite funny to read. So these are my hints. And I think we should start with the first presentation by James Ault, if you're fine with that, James.
Sure.
Thank you so much. Bye-bye.
Let me just get my screen sharing here. It was working a second ago. Oh, it's blocked temporarily. There we go. Cancel that. Now I can do it. Screen 2. Yeah, okay.
Yeah, working fine. Thank you.
Great. And switch over to this. All right. So my name is James Ault. We created a benchmark for reinforcement learning and traffic signal control. And this was joint work between myself and my advisor, Dr. Gunny Sharon, here at Texas A&M University. No, it's not skipping. There we go. So this talk is broken up into 4 parts. The first one I'll kind of skip because you give a very good description of reinforcement learning and traffic signal control there. Then I'll talk about why we needed a standard benchmark, and then our solution for a benchmark environment, and then how to get started with it. That's the domain section. There we go. All right, why we need the standard benchmark. So we found that state-of-the-art algorithms were difficult or impossible to compare for traffic signal control. 2 in particular, the feudal multi-agent A2C and MP Lite, both claimed state-of-the-art performance. But in the case of the first algorithm, the experiments were conducted on synthetic traffic demands without clear connection to more realistic scenarios. And in the latter, a non-standard simulator was used with traffic data estimated from recorded taxi trips. And in both cases, the implementations were unavailable, and the 2 competing methods had not been compared. And really, the choice of simulator was very difficult to compare. For instance, there's one author of a paper called IntelliLite, where they used the Sumo simulator, and then just a year later, they had used CityFlow in their PressLite paper. And there's some different results that they got for the same algorithm, just in different simulators. So there's a lot of different parameters that could have been the cause of that. But in general, I think the Sumo simulator is, much better established. So our benchmark environment, the reinforced signal control benchmark. So Resco is based on the Sumo simulator, which is open source and has been used for 20 years in transportation research. The benchmark includes 2 single agent tasks and 4 multi-agent tasks with up to 21 connected signals. These tasks were extracted from published traffic models for Sumo in 2 German cities, Cologne and Ingolstadt. The multi-agent tasks were divided into corridor and regional problems as well. You can see in the image here the areas of the cities used marked by the red boxes. And then in the corridor and region sections, you can see the red boxes show which intersections have traffic signals. As a lot of the intersections there are just controlled by stop signs, which this differs from a lot of the scenarios that you'll see in many publications on traffic signal control and reinforcement learning, where they just have a simple grid layout with no, like the roads connecting them in between, they're all assumed to be controlled by signalized intersections, which just isn't the case most of the time. So for comparison, we included 3 baseline signal controllers, fixed time, max pressure, and greedy. And greedy just takes the action with the highest vehicle count. So in addition to the 2 state-of-the-art mentioned before, 2 independent decentralized algorithms have also been included, independent DQN and PPO. And further, we validated the implementations of MP-Lite and FMA2C, the state-of-the-art algorithms, on scenarios similar to those presented in their publications, and found that the results were similar to what they published. So we're confident that the implementations are correct. So Resco makes it easy to implement new methods as it uses a GIM-like interface. The IDQN and IPPO implementations are directly called from an RL library built around GIM environment. Further, it allows you to define the state and reward through a straightforward interface. And as the benchmark tasks were extracted from publicly available scenarios for Sumo, new tasks can readily be created from more accurate traffic models in the future. While average delay is the most common reported performance metric, the benchmark outputs all of the common metrics, including those based in queue lengths, travel durations, and waiting time. The benchmark is not only quick to set up, but is also quick to run as it features libsumo support. Libsumo is a C++ interface for Sumo, which greatly reduces overhead, allowing for much faster simulation execution. Further, Resco has multi-threading support to facilitate executing many instances of Sumo, which is important when you have to run many experiments to get confidence intervals, which can be a pain to set up.
James, I'm not sure if I am allowed to interrupt you, but
sure, go ahead, please.
Questions in the in the chat.
Was that the sound I heard? I heard some sound, but I didn't know what it was.
Yeah, Anton asks, what is the difference between IPPO and PPO?
So since it's a multi-agent benchmark most of the time, so there are 2 single agents, but basically they're just there's no communication. IPPO is just PPO. It just stands for independent PPO. So PPO on each intersection with no communication in state or reward or any other coordination methods, basically.
And then PPO would be a case where we treat all traffic lights as one single agent. Is this the case?
Yeah, it could. Yeah, it could be defined that way. Really, there's not a clear way to demarcate them, I guess. Most people would just say it's based on however you define your state and reward at that point. But yeah, it's just trying to make it distinct that each signal in the multi-agent task here, like each of the red boxes, they have their own individual PPO agent. So the independent is trying to tell us. Okay, go back to the slides so I can change them. There we go. Oh, that was this one. So Resco is flexible enough to conform to sensing assumptions made from simple loop detectors to advanced camera-based sensors. The state space can be defined from a dictionary map to each intersection, which makes available a number of features. These include the number of arriving and departing vehicles at each intersection, the queue length, approaching vehicle count, aggregate waiting time, and longest waiting time in every lane. And for each vehicle, the waiting time, speed, acceleration, position, and vehicle type. Multi-agent algorithms typically include some form of communication, as both MP-Lite and FMA2C do. And to ease that implementation, a mapping of intersection adjacency is provided for all of the benchmark tasks. And the state and reward functions can be defined from this dictionary using all of the features or just a subset of them, depending on the assumptions made in the particular experiment. So the action space is similarly flexible. There's no limitations put on which faces can be taken, other than those which would conflict, causing traffic to intersect. For instance, phases 2 and 4 in the image here, that wouldn't be allowed because you have crossing traffic. The action space excludes the consideration of yellow signals because they're required for safety, which means that you don't have to, the agent doesn't have to say, or have to learn to put in the yellow signals through some mechanism. In this case, the actions are just choose a green signal, a pair of phases which don't conflict. So for this, Resco handles automatically and inserts the yellows when they're required. So by default, a chosen pair of phases is active for 10 seconds, with 3 seconds reserved for yellow phases. This setting, however, is configurable to the safety requirements for each signal.
But when you say configurable, do you mean that it's configured once for the environment, or does the agent get to decide what the interval is?
So it's not set up for the agent to decide that, though I have seen some works that use that action definition. The issue we have with having that as a standard feature is that algorithms which would share control with a single agent couldn't have differing action lengths. But when you try to set up the action space for that, it gets very messy. So it is possible to set it up to have an agent choose the length of actions, but it's not part of the benchmark currently.
Oh, but still, the agent in this setup, the agent can select the same phase as it has before, right? And
yes.
then
it'll just get another 10-second duration with no yellow.
Yeah, so that actually does allow you to configure the length of the interval in a way.
Yeah, no, in a way, you're right. Yeah.
Okay, thanks.
Mm-hmm. So we evaluated the benchmark test with all the algorithms and baselines included, and we found that the state-of-the-art algorithms have some significant shortcomings. Overall, we found that IDQN showed better performance than MPLite or FMA2C. MPLite often failed to converge, so we included an extended state space version of MPLite as well, marked here in yellow, which you see is only in the Ingolstadt singles signal. And we include that because it has a relatively simple state space assumption compared to the other methods. However, in most cases, it didn't improve the performance. In these charts, you can see the IPPO often exceeds DQN's performance. However, it requires far more training time, and in the full training curves, it is evident that it suffers from high variance. So just a note on these graphs, lower numbers are better because this is the delay in seconds, so you want to minimize delay here. And then the episodes are along the x-axis. And in particular, the Cologne quarter scenario, we see that the fixed time is much better than the baselines in any of the other scenarios. That's because the quarter really relies on having a green wave, which the fixed time settings were enabling already. So it already performs very well using just the simple fixed time.
Excuse me. Well, I'm familiar with the concept of green wave, but I don't think everyone is. So can you?
Sure. So the easiest example is say you have I can go back to these actually. So we have these three lights here in the corridor. This is actually the corridor that I was talking about. So a green wave would be a car that starts. Oh, I guess you can't see my cursor, can you? I think
we can see cursor, although it is quite small.
There we go. That should help, right? All right. So a car that's sitting at this first intersection would get a green light to go this direction, and say the car is heading all the way to this end. So then this light would be set up to give a green light in this direction when the car reaches here. So it's set up based on like the average speed and length of this road. And then this one's set up similarly. So basically it gets a green light every time it reaches another light. Hopefully that explains the green wave well enough. There we go. Yeah. So moving on, how you can get started with Resco. There's just 4 steps to begin training one of the included algorithms. Install the Sumo simulator with the first command. Grab the benchmark repository with the second. Install dependencies with the third. And finally execute the training program while specifying the algorithm and scenario. So in conclusion, we found that the state-of-the-art algorithms work well in the environments that they were designed around. However, the benchmark tests demonstrate that they may suffer in more realistic scenarios. The Resco benchmark enables easy comparison with previous algorithms while allowing for an easy interface in which to implement future methods. So thanks for taking the time to learn about our work. If you have any questions, I'd be glad to take them now, or you could reach out to me via email.
Yeah, thank you very much. I want to remind everyone that this offer is for everyone. It's not just for me and Tijs. You can ask questions. I do have some, but yeah, maybe Tijs wants to go first.
I have some questions as well, and I'd like to remind the rest of the audience that the next presentation will probably start at around 1600, because the author couldn't come here earlier. So we have quite some time to discuss and speculate where this is all going. So I'd like to see some questions in the slides. So here. A fellow Jitster, probably anonymous, asks whether the slides will be shared. The talks are recorded, so you can look this back on YouTube. Is there a question from the audience? Or I will start with a question that I have. James, again, thank you for the presentation. I was wondering, what are your future plans with the benchmark? Are you trying to add more networks or more algorithms?
So with the benchmark, we're not specifically trying to add more features to it right now. My future work is more focused on developing new algorithms to coordinate intersections and inside the benchmark. Particularly the Cologne corridor is of interest because as far as I'm aware, there aren't any RL algorithms that produce a green wave. So it'll be interesting to be able to do that.
Yeah, I was a bit confused by the charts when I read your paper. So thank you for the extra information that it's a green wave that's causing the fixed time to be so performant there. What do you think about a green wave typically works in one direction and the other direction suffers from it a little?
Right.
Do you think, is there an idea that reinforcement learning might help here?
Right. So I'm not a civil engineer, but my understanding is that the green wave, you would generally have it, so say at like 8 o'clock, the direction of traffic flows more heavily in one direction. So you would set it up that way, and then maybe 5 o'clock it's coming back, and you would change it that way. You'd have to set this up manually with traditional methods, but with reinforcement learning, you should be able to learn that the direction of traffic flow is changing, and the green wave would evolve back the other direction. But there is a separate issue of the arterial roads where you'll have starvation, which I think is actually goes into the second talk today about a fair reward, because so far that's not really handled here either.
Okay, thank you. I was also wondering, I was looking at your benchmark and thought, well, let's have our algorithms in there and check how well we perform. So I'm eager to go and experiment with that.
Excellent.
And now that you showed that it's really easy to get started, I will do so. Are you trying to get other people on board as well, or have you seen other benchmarks or other efforts in this field? That you
So we actually haven't seen any other benchmarks. This came about because there were so many different scenarios being used in different simulators, even, which it made it impossible to say, hey, all right, mine's doing better than that one. It's a potential improvement here because, between the simulators, some of them are very basic, where they don't have car following models kind of deals. So,
Do we happen to have somebody in the audience who is interested in getting his or her algorithm in the benchmark?
Yeah, I would really suggest doing something like a competition.
It's a good idea.
A lot of conferences have like calls for competitions where you can just submit your benchmark and make it like next NeurIPS competition or something. I'd really love to see it.
Yeah, there's I can link it for you.
Yes, this is a paper. I guess we can link to the archive preprint, right?
Yeah,
if
that
someone
would
wants
be
to
fun.
read it. I wanted to ask about the reward functions. So first of all, you said that the simulator, the environment does support different reward functions, right? So you can build your own reward function out of the data that we have there. But is it completely unopinionated? Do you have an opinion of what the reward function should be?
So ideally, sort of still ignoring the starvation problem and fairness to arterial roads. Ideally, it would be the actual delay that is the performance metric, but we can't really measure that in real time because we don't know what the delay of the trip is going to be until it completely ends. We can estimate it by the speed on the road and number of vehicles kind of thing, but to me, I just using the waiting time seems like the best reward. But even then, it still lacks a bit. So,
yeah, let's be more precise. And what exactly is the delay? Is it the amount of time that the car has spent on waiting for traffic lights?
It's not just the amount of time that it's spent waiting. It's the amount it's slowed by having extra traffic congestions on the route, which are caused by the traffic lights.
Okay, so essentially it is the length of the trip, right? But just minus some minimal length of the trip.
Yeah, so it's subtract from the average speed of the road that it would, like the free flow speed of the road minus the actual time, or the actual time minus the free flow.
Right. Okay, clear.
Yeah.
Also, by the way, I just note that we haven't said this explicitly yet, but this is a pretty clear case of multi-agent RL problem. So we have this game where we have these agents called traffic lights, and we have these agents called cars, and they are playing with each other, and we can use reinforcement learning on each of these agents. And we can also decide to join like traffic lights into a team or not join it. So this is a classic multi-agent RL setting.
Yep.
Also one thing that piqued my attention was that all of the cities are from Germany. Is there a reason for that?
So actually, the Sumo Simulator is developed in Germany, I believe, and that doesn't mean that they're from Germany, but that the scenarios picked are from Germany. The scenarios are just they're separately published. I can actually link. There's other ones too that aren't in Germany as well, but it just happened that Ingolstadt and Cologne were the most recent and advanced traffic scenarios in Sumo. So yeah, I didn't specifically pick them because they were in Germany. I just picked them because of the best data we had.
I just think I missed the point that this is your RL environment is basically based on another simulator, right?
Yeah, so the Sumo simulator, it's a micro simulator that handles the actual moving the cars around and simulating the actual intersections. So the benchmark is sits on top of that, and then but there's a lot of things that need to be handled between the simulator and then getting into an RL environment as well, which the benchmark handles. It wasn't. I probably should include something about the different simulators in this talk. I did, unfortunately. Sorry.
Yeah, but that's thank you for. I have done something like that previously too, where I have wrapped healthcare simulators that aren't really fit to be reinforcement learning environment. I had to wrap them, so I know that it is a lot of work to write this to make this wrapper, and this is as a resident reinforcement learning connoisseur, I have to say that it is a very common. So there are still a lot of good simulators that are waiting to be wrapped in a reinforcement learning environment. This is something we still need to work on, and a lot of like interesting research can come out of that. We have like physical simulators that can be used to optimize different physical processes. We have city simulators, we have economic simulators that weren't built for RL, and we can adapt them for RL.
Yeah.
And thank you, James, for making one more.
In the context of simulators, I have a big question, probably the elephant in the room, as they would say. James, could you say something about the sim to real gap in traffic optimization? Typically, we see a lot of research with simulators and then performing really well.
Yeah.
I'm also really interested in getting it on the streets. And what would it take, according to you, to get there?
So unfortunately, there hasn't been any work that I know of that has put RL actually controlling the intersections into a real intersection. So actually seeing what the gap is, I intuitively, I don't think it's that large because the simulator is quite advanced. It does simulate what actually goes on pretty well. What it comes down to is what the assumptions you make when you use the simulator. For instance, you could take the entire state space that I described and use that, but that might not match what you can actually use in real life. If you just have loop detectors, then you have very little information to work with. So yeah, that how large do we get there? It comes down to modeling specifically the intersection that you want to work with, and making the correct assumptions about it as well.
Yeah, so I was wondering, is it possible to do a lot of training in using simulators and then fine tune on the streets, as you see in say supervised learning? There's a lot of work
Right.
being done where you just tune a little on a big given.
I would assume that would work well, but as far as I'm aware, there haven't been any publications about it or any research done on it. So
Yeah, I've seen some companies that advertise that they're using reinforcement learning in the streets, but it's always really hard to tell whether they're actually doing it and in
Right.
what way.
right, how much of it is actually the RL, and it's just changing a number from 3 to 4 or something.
Yeah.
I wouldn't want to be standing at a traffic light that is just initializing the learning.
Yeah, there's a line of papers actually that try to reduce the pain of that, because nobody wants a traffic light that needs 10 days to get better than the worst static methods, because it's 10 days of reduced economic output, I guess. So it's no good.
Right, but then the simulators that we are using, they have car models, right? They have the algorithms that control cars. How data-driven are they? Is it just something that the developers dreamt up, right? Or is it something based on real behavior of cars?
Yeah, so I don't know too much about the car following models, but they weren't created by the simulator programmers. There were studies in civil engineering that were used in traffic optimization previously. So yeah, they are based in how cars typically drive at a high level, I guess.
Right.
In this context, it might be nice to mention there is a paper on inverse reinforcement learning. I am totally unfamiliar with this subject, but Vadim probably knows more about it, where they try to train a simulator from data. So instead of using a car following model or something similar, just look at data, perform inverse reinforcement learning, and then you get a kind of neural net based simulator. It might be interesting. I don't know how feasible it is. It's quite interesting research, I think.
No, what I'm thinking is, given all of those phones and all of this data we have on actual traffic, right? We can train a model of a driver based on the data, like a neural, like a deep driver that imitates how real drivers behave, and put that into a simulator.
It's quite hard. They're humans, so it's really hard.
You just have to model the human brain. What could possibly go wrong?
I think I noticed that Majid is also part of our audience now. So perhaps if we have another question from the audience, and if not, then we perhaps can go on to the next presentation. Is that possible with you, Majid? Or any other questions from the audience?
Hi, everyone. Yeah, it would be okay with me.
Okay. Then again, James, thank you very much. I really loved your presentation and the paper. So really nice to see this. Thank you.
Thank you for having me.
Thank you.
Then the floor is yours, Majid. Thank you.
Sure. Can I share my screen?
It's the third button on there.
Should be able to.
Okay, can you see my screen? Oh, I think it doesn't allow me.
Not yet.
Actually, it tells me that screen sharing failed, but I don't know what the problem is.
It could be authorization of your browser, because I don't think we have settings to.
So what happened to me was I clicked the stop sharing prior to actually using it, and then hit escape to make it go off my browser. So you look at the permissions on the URL bar when you click on like the camera and all that. It might say like blocked temporarily, and I had to click the X on that.
Yeah.
I don't know if that's what you're getting.
And also, one last minute fix we can do is you try in a different browser.
Yeah. Let me see if I can. Okay, I think I can join with another browser, so I might have to.
All right, you're listening to the end episode of Technical Difficulties. We'll be back with you shortly.
Okay, hopefully it should work now. Okay, can you see my screen now?
Yes.
Yes.
Okay, great.
Yes, everything is fine. Thank you.
Okay, no problem. Okay, so as you might already know, my name is Majid Raes. I'm a postdoc in Electrical and Computer Engineering Department at the University of Toronto, where I did also my PhD under the supervision of Professor Lynn Garcia. So my focus has been mostly on performance evaluation and also stochastic analysis and modeling of service systems like transportation systems and computer networks. Okay, and today I'm presenting one of our papers titled A Deep Reinforcement Learning Approach for Fair Traffic Signal Control. As you might already know, traditionally traffic signal controllers use handy engineered control policies which either are not able to adapt to the dynamic condition of the traffic or have very limited flexibility. But with the new advancements in deep reinforcement learning, actually, there is an increasing interest in using these algorithms to develop like dynamic policies for the traffic light controllers. One of the most common goals in these types of work is to either maximize the throughput or minimize the average travel time of the vehicles. But actually, there's another measure, another important measure, which is often neglected, and that is fairness. In other words, if we just focus on like maximizing the throughput or minimizing the delay, we will have situations where like some vehicles experience extreme waiting times, or this might be the case that, for example, the throughput of a particular traffic flow, for example, the west eastbound, will be heavily impacted by small fluctuations of another conflicting flow. So to tackle actually these problems, we first introduced two notions of fairness. The first one is delay-based fairness. This is particularly from an individual vehicle's perspective, where the goal here is to decrease the number of vehicles that experience long waiting times. The other notion is throughput-based fairness, which is more from the traffic flows perspective. And here the goal is to minimize the effect of conflicting traffic flows on each other. And this is kind of like an extension of the notion of weighted fairness, which is popular in computer networking context, where if this denotes the throughput for a particular like flow, for example, north, south, and west east, and phi's are and the phi's are, and the phi's are the weights that are assigned to these like traffic flows. And we want the normalized throughput for two different conflicting traffic flows will be equal to each other for a given time interval that both of these traffic flows have traffic. However, there is a problem here that we cannot achieve this like ideal, sorry, I don't know why this problem happens, that there's a problem that we cannot achieve this ideal like goal, and that is that the intersection cannot be used simultaneously to serve both traffic flows at the same time. So in computer networking, where like the units that we are serving are packets and we have control over packets, actually there are algorithms that can like put a bound on the difference between these two like expressions. However, here we also don't have like explicit control on like particular vehicles, and the other thing is that we cannot like serve the traffic flows vehicle by vehicle, because the traffic lock has to stay for one phase for minimum time interval, and we shouldn't like frequently change the traffic light. So the goal here is to minimize the difference between these normalized throughputs for the conflicting traffic flows. So in general, the goal that we have in this paper is to kind of provide a balance between the system's throughput and the fairness. So the first controller or algorithm that we propose here is to provide delay-based fairness. The state that we are considering actually consists of the queue length, which is the number of vehicles that are waiting behind their red lights, some of the waiting times for those vehicles, and the current phase. Now, what's important here for us is to only consider states that are like that can be measured in real-world situations, and also we don't want to like consider many different states because it increases the state space. And one thing here that might seem that we might not be able to capture or measure in real time in real world situations is sum of waiting times. And here we actually propose an algorithm to just estimate it based on the sequence of queue lengths. Actually, here we're assuming discrete time, which is the time slots that we are taking the actions. And for example, if you assume that the light has just became red, the sum of waiting times for the vehicle just becomes the queue length of the vehicles that are waiting for the first time slot. Now, for the next time slot, the ones that join waited in the previous time step has waited for 2 time slots, and the new ones that have joined have waited for 1 time slot, and so on. And here we can like provide a recursive algorithm to compute this sum of waiting times. Now the action here is to choose one of the phases, whether green west east or green north south, and we are only considering one particular intersection with these approaches, and phase 0 is the green for west east and phase 1 is green for north south. For the reward, actually, let me first introduce these parameters. So dnt is the partial waiting time of vehicle n up to time t. And w sub n is the total waiting time of that particular vehicle n at the intersection. N sub t is the set of all waiting vehicles at the intersection at time step t, and n is the set of all vehicles in an episode of our like learning algorithm. Now we define the reward as here, reward for time step t. It's the sum over all the vehicles that are waiting at the intersection at that particular time step. And for each vehicle, we compute this expression where dnt is the partial waiting time up to that time for the vehicle n, and alpha is just the hyperparameter. Now, to just give you an intuition why the logic behind designing the reward like this is that if we calculate the contribution of each vehicle in cumulative reward. It's actually being shown in the paper that for each vehicle, it will be minus Wn, which is the waiting time of that vehicle, plus alpha squared of Wn. And it's like considering the waiting time for that particular vehicle and its squared value. And when we are like calculating the total return or the sum over all the rewards over time in an episode, it's like considering all the vehicles. So we have the sum over n for Wn and also Wn squared. Now here is the return or the expected total return that we want to maximize. And as you see, the first term is the expected sum of delays that we need to minimize. And the other one is the sum of squared values of delay. So it's like, this actually, the second term corresponds to the delay-based fairness. And the reason is that if one of the cars experiences a large delay, it will actually penalize the algorithm, to penalize the controller. Another also intuition is using the James Fairness Index, which is usually used to measure the fairness. It's the sum of Wn or whatever our measure is to the power of 2 over n times sum of squared values of Wn. And as you can see, this one, the numerator actually corresponds to delay-based fairness, and denominator is proportional to the expected sum of delays. And the maximum, and the second algorithm that here we are proposing is the throughput-based fair controller. So here our state consists of these parameters. We consider the number of vehicles in L meter vicinity of the intersection, which is like shown here. And so we actually use this to see if a particular we have traffic in a particular direction or not. The other parameter is fairness deviation of the conflicting traffic flows, which are like north, south, and west is flows here. And it will be defined as the sum of the difference between these normalized throughputs for those directions times BT, where this BT is actually just a flag. So it's 1 if both of these directions have traffic, and it's 0 otherwise. And that's because we only care about fairness if both of these like traffic flows have traffic. Otherwise, we can just give the right of way to the direction that has traffic. And finally, we are using the current phase. The action is similar to before. We want to choose one of the phases at each time step. And for reward, actually we are using Q sub KT, where K actually denotes the approach. And Q is the Q length for that particular approach at time T. So we define the reward, the immediate reward at time step T as here, which is the summation of Q lengths for all the approaches minus beta. And then we have this fairness deviation, the absolute value of fairness deviation. Now, again, if we compute the total return or the sum of these immediate rewards over time, we can see that we can rewrite this as, again, the expected sum of delays minus beta, which is a hyperparameter, and then expected value of sum of fairness deviations. So it's like the second term actually corresponds to the throughput-based fairness, and the first one is the expected sum of delays. Again, we can see the trade-off here, where we can use parameter beta to adjust this trade-off. Now here are some of our experiments. For the baselines, actually we're using two traditional methods. One is self-organizing traffic light, which is a threshold-based method, and the other one is max pressure, where in it actually gives the way to the direction which has the maximum pressure, and the pressure is defined as the difference between the Q lengths of different like lanes of the approaches of that like traffic flow. Now, here are the parameters that we are using for our environment, and we are using Sumo for simulating the environment. For the arrival traffic, actually we use different distributions. So usually what other studies are using is mostly like Poisson distribution for the arrival of the vehicles. Here we're considering two other also distributions which might be more realistic. One is here we're using Markov modulated Poisson process, which actually can create bursts like to simulate like platoons of car. And also in the next experiment, we're using non-homogeneous Poisson process, which can be time varying and non-stationary. And the algorithm that we are using is double deep Q network. And here are like the parameters for the arrival rate for each direction, and also the probabilities of changing between states for the Markov modulated Poisson process. So the first row of figures actually shows the performance of our algorithm, DFC, the delay-based fare controller, for two different like hyperparameters. 0 is the case where we are not considering the fairness, and 2 is the case that alpha equals 2 and we are considering that. And here we're showing the 95% quantile and also the maximum waiting time as a function of the episodes, as the algorithm learns. And as you can see, as the number of episodes increasing, DFC2 has a much better performance compared to the red one, where we are not considering fairness. And as you can see, the maximum waiting time increases for DFC2 is much smaller than the one that we are not considering fairness. Another comparison is the figures in this row, where we're actually showing the CDF or cumulative distribution function of the delays for different algorithms. So, and also these like points show the maximum waiting times. And as you can see, for DFC2, the tail of the distribution is minimal. So in the first figure, which is for the west is east-west bound, you can see that DFC2 has the minimum like tail. And for the north-south, you can see that DFC2 and also max pressure have the minimum tails. So as you can see, for both like directions, our algorithm has been able to produce waiting times in such a way that not minimize, but compared to other algorithm, like reduces the tail of the distribution, and so the vehicles experience less like long waiting times. And the other experiment is where we are considering the effect of different traffic flows on each other. So here the west is east-west bound has Poisson distribution for the arrivals, but the north-south node has non-homogeneous Poisson process where we have a periodic changes or surges in traffic. And here is the parameters for the period and also the values that the arrival rate can get. So the first row shows the throughput for the different traffic flows, west, east, and north-south for our algorithm for max pressure and SOTL. So as you can see, although the north-south traffic has surges in it and changes, it doesn't have that much effect on the west-east traffic as we wanted. But for the other two algorithms, we can see that it heavily affects the throughput for those directions. Also, in terms of average waiting time, we can see that our algorithm can achieve a much better performance for both directions, while max pressure and SOTL can result in like large fluctuations of average waiting times compared to our like algorithm. So that was a brief overview of our paper, and thank you very much for your attention.
Thank you very much. It was
Thank
really
you.
nice. We still have quite some time left for questions. I have some, but perhaps I will allow the audience first to ask some questions or have some remarks. Perhaps James, are you familiar with the work?
Yeah, I think it's very interesting. So I saw that you had the queue length in the original slide there, and then you related it to the waiting time, right? But then, I'm trying to think back to your slide here. I think you have hyperparameters there, alpha on the first slide and beta on the second one. Are those just hyperparameters, or how do you set those?
Yeah, so these are actually for just balancing the trade-off between the fairness and throughput. So in the extreme case that alpha or beta is 0, it's like you're not caring about fairness, and in the
Right.
extreme case that they were very large, it's like your primary goal is just fairness.
Okay.
Yeah.
So then, is there? How did you choose those values then?
So actually, I think it depends on the application and how much it will be important for us. So in some cases, if we increase like those hyperparameters, it might result in cases that it jeopardizes the throughput very much. So I think it's up to the application and the situation that it's being used. Yeah.
I see. Thanks.
Majid, would you then also be able to extend this to other policies? For now, you're comparing your fairness for two directions, but if we add, say, pedestrians into the mix, completely different.
Yeah. Actually, it will be. It should be. We should be able to do it for the cases that we have like other conflicting traffic flows, even not pedestrians. We can have like turning right or left. So here we're just considering a basic scenario where we have just two conflicting flows, like north, south, and west east. But there can be cases that we have like multiple conflicting traffic flows, and we can assign like different weights to each of them and consider it. So this is mostly for our second algorithm, which we are considering like fairness at the level of traffic flows. But the first one, the main focus is on the waiting times for a particular vehicle. So it's from an individual vehicle's point of view, the first one.
So perhaps I can check if I understand it correctly. You are using these different arrival distribution sets just to show an interesting scene. But I was wondering, you test this and then compare it to baseline algorithms. But then I thought, perhaps is there a risk that the neural network is training or learning the distributions, the cycle in the distribution? Do you think that's an option? Is it possible to, say, test it on another distribution and see how it performs there? Or I have some background in supervised learning, where I see you have this testing and validation, and it's all quite rigorous. And in reinforcement learning, I understand that it's way harder to validate something. So could you say something about this?
I see. Yeah, actually, that's a very good point. So unfortunately, I think we haven't done like learning on one distribution and testing on another distribution, but that's a very like interesting comment that we have to work on. But yeah.
Perhaps to get James in the mix as well, how do you think about this? Because you are now comparing different algorithms in a rigorous benchmark. So I think that's a really nice step. But I also read in your paper you have to validate these algorithms. So you check them against the papers and see if your implementation is correct. But if you look at this dimension of validating and testing algorithms, especially again with an eye towards practical implementation issues. How do you think? What would be a good way forward, or is there research that we should look out for?
So we don't have to rely on just generating traffic movements in the simulator with just distributions. In particular, the scenarios in the benchmark, they're based on like observed traffic data over a period of time. So I guess you could that's it. The hope is that we learn those distributions automatically. So the RL agent learning the distribution isn't a problem for us. That's our goal. But yeah, having a complicated enough simulator is important to make sure that we don't just fit a single distribution. So I actually had another question. You're showing those the graphs of the sort of the overall result graphs with the blue and yellow lines before. I see you compared it just to the max measure and state of whatever SOTL stands for. I never remember.
Self-organizing traffic.
Yeah, there it is. Yeah. So did you compare that to like different values of the hyperparameter as well? Because like we see that TFC works very well on those, but it would be interesting to see how TFC works with different values. So like if you set it to 0 where you just have a completely unfair learned agent. Yeah. Or maybe I missed that graph. Yeah, sorry.
You mean comparing TFC with hyperparameter 0 with SOTL and other like baselines, right? Yeah. So for this experiment, actually, we wanted to show like the capability of TFC to provide this fairness. So the main goal was to find an hyperparameter which results in the best performance. But yeah, it can be done that we also add like TFC with different like hyperparameters to see how fairness can play a role here.
Thanks.
I absolutely have to ask you about the sim-to-real gap. Because apparently you're using as your simulator some assumptions about the distributions of distributions of cars come into an intersection, right? The Poisson distribution or something. So we might expect that if we transfer, and then we can't transfer an algorithm directly into real life from that, right? Because the distribution isn't exactly the same. So what do you think are the steps required to basically go from your experiment to actually using these approaches in actual traffic lights?
I think, as James mentioned, the better approach would be if, for example, if you're interested in a particular intersection in a real world, we can first gather data for the traffic and then use it for generating the traffic in the simulator. And then based on it, like learn our algorithms instead of just using like mathematical methods to generate the traffic. But here, because the goal was just to show the importance of fairness in the traffic light controller, we actually our main focus was on fairness in different situations that we can have, for example, time varying arrivals and things like this. And in order to be like repeatable, these kinds of things, I think it was important to just choose mathematical models to produce the arrivals or have the inter-arrival times. But yes, for the next steps that we want to actually use them for real-world situations, I think the next step would be to use like real-world data for the arrivals of the vehicles, and then based on that, learn a model and then fine-tuning for the real world situation.
Right. Yeah, thanks. I also think that actually combining your work using your fairness-based reward function in James's environment might actually be a very interesting step.
I have one further question. I read that you are using a neural network of 2 layers with 32 nodes. Is that sufficient, or are you expecting a larger and larger networks in the future?
Actually, for this case that we are considering just one intersection, I think it's enough. And even I think in the case of like reinforcement learning, adding more layers might even jeopardize the performance in some scenarios. So I think for our case, it was enough. But yes, for more complicated scenarios, or if our state changes, for example, if you're using images of the intersection, that might change, and we can have like more layers for our neural network. But currently, that our state space is, I can say, not that big. And also we are considering just a small intersection. I think that would be enough based on our scenario.
So I'll just add that it's very common in traffic signal control, or basically reinforcement learning, traffic signal control. They have very small networks. It's actually a massive advantage to those that don't have insane funding like DeepMind. So we can actually do work. So
Yeah. Yeah, because James, I saw a lot of diverging charts in your research. Has that to do with the neural nets being too large, or just is that something
no,
else?
actually the neural networks are fairly small that are benchmarked there. Even in the state of the art, like MP Lite and FMA2C, they're still very small. I don't have a great explanation for why they diverge so much. Yeah, I think it's more algorithmic sided though.
Perhaps somebody else with some other backgrounds. I'm hearing rumors that in robotics there are some advancements where you have more of a guarantee for neural networks, or for reinforcement learning, to actually provide some guaranteed success when you apply it in the real world. I've seen these images of drones flying through forests, and I'm not sure whether we're there yet with traffic control. Do you have any idea, or Vadim perhaps, on research in the robotics? Where do these guarantees come from, and is it transferable to this field of research?
I mean, we had the seminar on the sim to rail gap in robotics, so I'll just refer you to that. But
Thank you.
basically, there is a way to there is a way to learn what the gap is. There is a way to actually compare what happens in your simulator and what happens to real life. You can record this log basically of what happens in your simulator, and then what happens when you try it on the real robot, and you can use this to train a model that will help you bridge the sim to real gap. There is a lot of interesting research there. I'm not sure about like 100% guarantees though, but there's definitely sim to real gap is something that can be measured and learned, and a model can be trained to make predictions there.
Yeah. And then, Majid, I'm interested. Are you continuing with this research, or are you focusing on other areas as well?
Actually, right now I'm more focusing on accident prediction, so it's a little bit different from my current work. But yeah, I might someday return to this work again. But yeah, my main focus is here right now on predicting accidents and coming with like real-time risk maps for the city.
Okay, interesting. And is that also reinforcement learning based, or is it more in supervised?
No, I think it's more like based on supervised learning and perhaps graph neural networks.
Aha. Those might be an interesting topic as well, graph neural networks, but not for the reinforcement learning seminar. And then James, I was wondering, you mentioned that you are also investigating control algorithms yourself. Have you struck gold already, or have you found an interesting?
Not quite yet. Hopefully very soon.
Okay, I'll keep checking then. Thank you.
Excellent.
I wanted to ask our fellow Jitster from University of Southampton, is there anything we should read about from your research? Because apparently you're doing something similar, right? Okay, there might be a way, I guess. But yeah, if you shoot us like the paper or something, I'd be also interested to know what the research is there, because this happens sometimes that actually like interesting people come to the seminar, not just the speakers but as the audience as well. Also invites everyone like to collaborate in the future if you found something interesting here in the seminar. So yeah, anyone else have questions? I guess not. Then shall we wrap this up? Yeah, thank you, James. Thank you, Majid. Thank you, Tijs. And hopefully see some of you at our next installments. Until then, have a good weekend.
You too.
Okay,
Thanks.
you too. Bye.
Thanks. Thank you, James, Majid, Fadim. Bye bye.